Okay guys, I told you that I was going to give you an example of calculating force on an oddly shaped surface. In this case, what we're going to do is take a triangular wall, and now imagine this as a trench that's coming up out of the page at us, and it's almost all the way filled up with water. This is a triangle with a height h, and then a width at the base here that we'll call B for base. Okay, and we want to find the horizontal pressure for the net, that's important, find the net horizontal pressure force on this triangular wall. Now a few things just to establish our boundary conditions. Let's set z is equal to 0 up here at the top and z equal to negative h down here at the bottom. We're doing that just to make life easier for us because now at z equals 0, P is equal to P atmosphere, or P naught is why we're doing that. And then down here, the width equals 0, and up here, the width equals B for base. All right, those are our boundary conditions. And we know that our expression for this force is now a couple things here. I said find the net horizontal force. That means that it doesn't actually matter whether this triangle is exactly vertical or it's leaned back, because regardless, we're going to be calculating the force on the horizontal projection. Okay. Now, the normal force here, so if we imagine the wall, this triangular wall is like this, right? So the horizontal projection is like this. So the normal force of it goes out like that. In that case, this normal vector is negative e of x. And then P will equal P naught minus rho gz. Now, quick check with our boundary conditions. When z is equal to 0, P will be equal to P naught, or atmospheric pressure, which that is how we set up our boundary conditions right there, so we know that this expression is valid for the way we set things up. Okay, I'm going to make a couple simplifications here just to make life easier. One of them is that I am going to just assume we're going to find the magnitude of the pressure force and not deal with it as a vector, so we can just ignore the normal expression. And the other thing is, since we're doing a net horizontal pressure force, if there is air on the other side of this wall, which there is, then I'm just going to go ahead and get rid of this and call this P net instead. It would be the same as the gauge pressure, the net pressure, the same. And what we get is FP is equal to negative rho gz ds. All right, that's all well and good. And you might be asking yourself, how is this going to end up different than just the vertical wall we did in class? Why did you tell us that weird shapes would end up different? This is why. We can't simply say, in this case, ds is equal to dy dz. We can't do that because our dy or our width is going to change with z because it's not a rectangle. What does that mean? That means that we will say instead that ds is equal to width, which is a function of z, times dz. All right, and so what is wz? I'm just going to sort of figure it out by inspection for right now. I know when z equals 0, w equals b, so that's b. And I know that when z is equal to negative h, which should be 0. So let's put negative bz. All right, so checking real quick, z is 0, we get b. Z is negative h, we get 0. Perfect. It's going to simplify that, and we'll get b times 1 plus z over h. Beautiful. So now we have an expression for w as a function of z, which means we also have an expression for dz. And that means that we can take this and we end up with z. I'm going to pull out all of the constants. Okay, so that's our setup. What are we going to integrate over? What range are we going to integrate over? We are going to integrate from negative h to 0. Okay, and we get negative rho gb times 1/2 z squared plus 1/3 z cubed over h, evaluated from negative h to 0. So we have 0 minus a negative, so positive, is equal to rho gb 1/2 h squared. Negative h cubed is negative h cubed, so minus 1/3 h squared. Turned into a squared because it's h cubed and I divided it by an h. Okay, that's our expression, which we're going to simplify into rho gb times 1/6 h squared, which becomes 1/6 rho gb h squared. Hopefully that helps. And this general procedure should work whenever you have a surface where your width is changing with z and you're trying to find a net horizontal force.